be possible to tune the interactions between pairs of these qubits. And one reason this is of interest is that a two-qubit interaction is a key element of a universal set of quantum gates. So we know that single spin qubits can be coupled using the Heisenberg exchange interaction, but for qubits with multiple spins, various strategies can be used. And one common method is to introduce additional spin couplings between spins belonging to different qubits. And this type of coupling between two spin cluster qubits translates into an effective exchange interaction between two spin one-half objects. And so the exchange can be controlled using methods similar to those for just two spins. Now, one realization of a spin cluster qubit is an antiferromagnetic molecular ring. And a method of controlling the effective coupling between these rings involves transitions between the two-qubit space and higher excited states in order to switch the effective coupling on and off. It's also been demonstrated that a uniform spin chain acting as a spin bus can be used to achieve long-range coupling between qubits. In our case, we want to find a mechanism by which the flying spin qubits and dimerized Heisenberg spin systems can interact in a controlled way. And in order to do this, we can encode each qubit within a closed ring. And what we find is that the domain walls themselves provide a mechanism for controlling the exchange between the qubits. So to see how this works, we can consider a pair of Heisenberg spin triangles with domain walls and a single antiferromagnetic spin-spin coupling between them. And we can look at the system in the basis of these product states, which depend on the two domain wall positions, but which are the two qubit basis states in terms of spin. And so the Hamiltonian for the whole system consists of both the coupling within the triangles and the inter-triangle spin-spin coupling. And if this spin-spin interaction strength is much smaller than the energy gap above the ground state for each spin triangle, then we can write an effective Hamiltonian which acts in the space spanned by these states. And here you can see that the effective exchange is isotropic, and it depends not only on this spin-spin interaction strength, but also on the positions of the domain walls within the triangles. And we can write the effective exchange in this form, which shows that for a fixed value of Jr, it's precisely the product of the spin densities at the sites involved in the coupling between the triangles that determines the exchange between the qubits. And from this plot, you can see that that exchange can be either antiferromagnetic or ferromagnetic, depending on the domain wall position, even though this spin-spin coupling is antiferromagnetic. And here you can see the exchange splitting in the energies of the lowest four states. And you can see that there's a relatively large gap separating the two-qubit space from higher excited states for all domain wall locations. So the effective Hamiltonian description stays valid.
I'm a little bit...
Yeah.
So physically, you're moving a domain wall in one qubit and a domain wall in another, in one ring and another ring, right?
Yeah, moving in the sense, yeah, varying.
Varying where they're located.
Mm-hmm.
In that 5A and 5B. So physically, why, can you go back to the previous expression? Yeah. So why is it that somehow that changes your interaction from being anti to ferro or whatever?
So actually, I'll go back a little farther. Maybe it's a little far.
Oh, maybe it's... maybe it's
I didn't think it was that far. Okay, so basically if you look at the spin density for these types of systems, you see that it alternates between positive and negative.
Right.
And so basically it's like, if you think of a classical system, it's like the spins being parallel and anti-parallel around the ring. Mm-hmm. And so if you couple, for instance, okay, now I'll go forward.
You go back to the...
Yeah, sorry.
So it's an overlap between spins that have various up and down, you mean?
Right, so it's like if you have, so for instance, normally if you just have two single spins, if you couple them, you have antiferromagnetic exchange. But if you now have, if you shift the spin density within one of the rings, then you get the opposite spin on the adjacent site. So it's like switching the sign of the effective exchange between.
And the effective exchange is only between that one spin there, that one, the sort of the center one? Or is it between all?
No, it's actually between the logical qubits that are represented by these triangles. So
no, but the JR, the physical JR.
The physical JR itself is antiferromagnetic.
And that's between?
And that's between, individual spins.
So it's also between, say, 1A and 1B?
No, it's not.
It's
not
just
in this
3A
case.
and 3B?
Yeah, I mean, you can add that kind of term, but in this case, I didn't put it in.
Okay. So you're assuming there's only that one term?
Right.
Between 3 and, okay, now I understand. Right.
Wait, that's what you did? I thought it was an effective coupling between the...
It is.
It is.
Yeah, it is.
After.
No, but...
But if you look at this
expectation values.
system in this 2-qubit space, then it's an effective coupling. If you look at just this term, it's one term in the exchange Hamiltonian. So is that?
You're building a ferromagnetic effective interaction from an anti-ferromagnetic single spin interaction.
Single spin interaction. But it's only between those two
So
spins.
that's not...
And then what you're doing is altering how much density is on those spins.
Yeah, the sign of the density.
The sign of the density. Okay.
Which is what happens if you move the domain.
Is this an experimentally realizable situation?
Yeah, and in fact, I'll actually get to that in a little while. But we think that it's possible based on what's been
You've
done.
got 3 spins in a dot.
Well,
3 spins in a dot.
No.
it's not. It's
3 dots.
So what we imagine single electron quantum dots.
Oh,
That we could configure.
The blue blob is...
So
A
this,
dot?
yeah, so this would, you could say it's a dot. Right. It's a spin in one dot.
Of 2 levels of... All right.
Okay. So far we've looked at a specific analytical model for the exchange coupling within spin triangles, but we can also generalize the results by considering larger Heisenberg rings with spin 1/2 ground states and different exchange profiles. So for example, we can consider a pair of coupled 5-spin rings which each have this domain wall, which each have this exchange profile with a domain wall at site 3, and we can numerically calculate both the effective exchange and the corresponding spin density variation at site 3A for the spin-up ground state as a function of the domain wall position within this ring. And here you can again see that the effective exchange can again be either antiferromagnetic or ferromagnetic, and the exchange and the spin density exactly satisfy this relation, which is of the same form as the one for the coupled spin triangles. And so we again see that the spin density variation between the rings within the rings determines the effective exchange between the qubits. And this method is in fact analogous to techniques that have been used to synthesize ferromagnetic crystals of organic radicals. And in these systems, the unpaired electron in the radical plays a role similar to a domain wall qubit, and stacking these radicals in different relative orientations gives rise to both ferromagnetic and antiferromagnetic intermolecular exchange.
So I still want to ask my
What gives
question.
rise to that odd shape for your plots?
For this?
Yeah,
So
it looks very asymmetric and it's...
Yeah, so this is actually coming from the form of the exchange profile that we're using. So this is like the domain wall in the flying spin qubits systems that we looked at. So it doesn't really look as neat as the analytical model.
When you talked about this domain wall being robust to disorder, what percentage of disorder do you usually
So
put in?
it's actually up to 50%.
50% disorder.
50% disorder, multiplicative disorder in the exchange.
I still want to ask my question. So should I be thinking of these blue things as quantum dots?
Yeah,
Someone
so
put
you
on a
can, in an
substrate?
implementation.
And the interaction JR is literally between 3A and 3B in
Right,
your modeling?
right.
Can you arrange that?
Okay, so, well, maybe not for, we were not sure about this.
Well, not Vanita, she's a theorist.
but,
There's no point,
experimental.
there's no
You took my
point making
line.
models of things.
I was being really nice.
So, well, okay, so, I mean, as I mentioned in the context of the flying spin qubits, it's possible to create these dice-type arrays of quantum
Okay.
dots. And so we think that it might be possible to, configure these dots in configurations like this.
Yeah, I'm not asking about the practicality of laying these quantum dots down on something. I'm asking about the reasonableness of the Hamiltonian that you're using to describe that array.
Oh, okay.
So if the distance between 3A and 3B is larger than the distance between 3A and 4A, then you can reasonably make some product ansatz for this. On the other hand, if that's true, then the distance between 3A and 3B is comparable to the distance between 4A and 3B, and therefore this model is completely inaccurate. We need all the possible interactions.
Well, I mean, you can make the distance between 3A and 4A much, much smaller than the distance between 3A and 3B.
Right.
So in that
Therefore-
case, this would hold.
No, then it wouldn't hold. Because the distance between 4A and 3B equals the distance between 3A and 3B. And so there's another coupling.
Oh, okay, I see what you're saying.
Yeah.
So that there's an equal.
Right.
But
You have to
these
couple all of them
these
together.
fall off exponentially.
Right.
These couplings.
I think he's saying that.
Separation.
Yeah. Well, okay, so if these two dots are extremely close, then you're saying that the distance, if the distance is the only thing determining the exchange,
Yeah.
then they would be
Yeah. So
similarly.
to me, that looks like an inconsistent model. What you want is all the pairwise sums of things, which then gets replaced with some effective interaction where you have a blob on the left and a blob on the right,
Mm-hmm.
and you allow these things to interact with each other. This is, it looks unphysical.
Well,
But,
I mean, you
but
can.
if you can use electric fields to tune the coupling, can't you change the
Right.
tunneling barrier between 4A and 3B? I mean,
Yeah,
it's
so-
not physical distance, right? It's-
Right, it doesn't have to be the distance as the only parameter that you use to control the exchange. That doesn't have to be the only thing that turns on the coupling between spatially separated spins. So you could have, say, you could increase the tunnel barrier between two, one of this dot and this dot, for instance, and decrease it between these two dots, and you could still try to achieve that kind of system.
But then are you back to trying to control things on very small length scales?
In this case, yeah, probably you would have
That's
to.
quenched. This is a quenched system. It's not like you have to modulate those couplings. You just have to design a system that will have them once through whatever fabrication technique, which is different from control exam.
Okay.
So I mean, okay.
So you could make a more conductive channel between 3A and 3B, for example?
Right, or
to enhance
another. I guess another possibility is, I mean, you don't have to have just this one coupling. That's not a requirement for effective ferromagnetic exchange. It's just like you can sum the terms, and if it still gives rise to effective ferromagnetic exchange, you can get that result.
Right. So that's actually a result from the spin cluster qubit work, is that actually
Right.
you can add that 4A, 3B coupling,
Right.
but it doesn't change. I mean, it will only make a slight change to the effective spin-spin interaction between the two.
Right, you
cluster
don't have to
qubits.
have just this one interaction. Okay. So we can also use spin triangles with domain walls as building blocks in order to construct an effective antiferromagnetic spin 1 chain, which can be thought of as a spin 1/2 chain with alternating ferromagnetic and antiferromagnetic exchange interactions, where spin 1/2 pairs coupled by strong ferromagnetic exchange act as the effective spin 1 objects. And so to construct this type of system, we can let the two domain wall phases alternate between two values. And here you can see one possible configuration of of domain wall phases and spin-spin couplings between the triangles, which gives rise to effective alternating exchange. And in this case, these pairs of spin triangles form the spin 1 objects. So we numerically calculated the lowest energy gap as a function of this effective exchange ratio for a 4-triangle chain with couplings of this form and periodic boundary conditions. And we found that the gap is finite, which is what we would expect for an antiferromagnetic integer spin chain. And we can also approximate this 4-triangle chain by an effective 4-qubit Hamiltonian. And we find that the error in the lowest gap calculated using this approximation is relatively small, and it falls off rapidly with the ratio of these two spin-spin exchange constants. So in order to verify the effects we've described here, we need to be able to implement them in a physical system. And one possibility for the case of the effective spin 1 chain is to use an array of quantum dots containing single electrons. But in this case, the dots don't need to be elliptical as they need to be for producing flying spin qubits. They can just be circular. And so we can reorient the triangles like this, and we see that we still have the required alternating ferromagnetic and antiferromagnetic exchange interactions, which you can see from the signs of the spin density for the spin-up ground state that are labeled here. And since it's possible to create these precisely controlled arrays of quantum dots, if we can construct an array of this form, then the electron spin exchange resulting from the variation in the distances between the dots can in principle produce an effective spin 1 chain. So now we turn to the second part of the talk and the spin-orbit interaction. So we've seen that spins and their interactions can be thought of as naturally existing elements of a quantum toolkit for the construction of these designer quantum materials. And one of the features that emerges in these types of constructed systems is that we can manipulate spins without having to apply magnetic fields. And we've already seen examples of this for the case of multi-spin qubits and spin-spin exchange interactions. So now we can add another element to the quantum toolkit, and that is the spin-orbit interaction. And this interaction has been very widely studied in the context of controlling spins using electric fields, and several proposals have also been made for carrying out single spin qubit gate operations using spin-orbit coupling. So to see how all this will work, we can consider basic properties of the spin-orbit interaction. So for an electron, the spin-orbit interaction describes a coupling of the electron spin to its spatial motion, and it has this general form. And if we compare this Hamiltonian with the Zeeman Hamiltonian, then we see that this spin-orbit interaction describes a coupling of the spin to an effective magnetic field. But now this field is momentum dependent, and if we consider the case of a one-dimensional system with a perpendicular potential gradient, then reversing the momentum also reverses the direction of this field. But now we can control this effective magnetic field using an electric field through the potential gradient. So the specific type of spin-orbit coupling that I'll be focusing on here is Rashba spin-orbit coupling, which comes from inversion asymmetry in the potential confining the electrons that's external to the crystal structure. So if we can control spins using electric fields, then it's also of interest to see whether we can perform electron